Okay, good afternoon to everybody. First of all, I would like to thank José-Alain Sahel for inviting me today and giving the opportunity to present the last data of my lab. So my talk is going to be more on the point of view of developing optical approaches. So you have seen that already in the past talk that there is a very large number of optogenetic tools that we can use to precisely activate or inhibit neuronal activity, and a difference in with different absorption wavelength or sensitivity, and also that there are a lot of techniques now that permit a very precise genetic targeting of those tools. So in my lab, as we are a lab mainly of physicists, the question is, given this large possibility of fantastic tools we can use in optogenetics, is there an optical way of illuminating them? And we are particularly investigating a number of optical approaches that try to answer to this question, which are based on the idea of going through an engineering of optical wavefront. And specifically, the one I'm going to present you today is called computer-generated holography, that has been already shortly introduced by Jens in the talk before. So in the first part of the talk will be really dedicated on guiding you through the advantage and the capability of this approach. And then in the second part of the talk, I will show you first some preliminary data that we are having in collaboration with the group of Serge Picot, where this approach is used to investigate the retinal circuit. Okay, so the first question is, which is the optimal illumination method to be used with optogenetics? So you have seen in the past talk, and also if you are familiar with the literature in optogenetics, that there have been already a very large number of key questions that has been solved by combining optogenetics with relatively simple illumination method that consists in using lamp or optical fiber or LED, and to shine visible light in large brain or in large volume, in large illumination volume. And the reason why those approaches work is because of the genetic targeting. So even if you send light in a non-specific way, but if you can record a certain response, you can be sure that this response came from this specific cell type. Okay, but today here in this symposium, the goal was to discuss what we can do with optogenetic and visual restoration, or in general what we can do by using optogenetic to restore damaged circuits. So if you want to restore a damaged circuit, one important step you have to go through is to understand how the circuit works. And so this includes, for example, understanding how different neurons or different cells in a certain circuit are connected between them. And then also what is crucial is to establish, for example, is there a critical number of those cells that they need to activate in order to evoke a physiological response, and thus this has to be done with a specific special temporal patterning. And something also that is difficult to assess if you just shine light in a non-specific way is the synchronicity of the activation, which on the contrary is something that might play a key role in controlling physiological activity. So if you want to enter in this kind of question, you need a more sophisticated approach where you can precisely control the light through the objective and in the sample plane, so to precisely target a single cell or a specific group of cells. And so you have to build up this system, and the question now in this talk will be, which are the main challenges you have to face if you want to build up this ideal optical system. And so here I have linked the one I consider are the main challenge we wanted to solve in the past year. And to really understand what I mean with this challenge, probably what can help you is to look at this film. So this is just an exemplary movie, but there are many of them, where this comes from the lab of Vincent Bonin in Belgium. So here what they did was to image the activity in the visual cortex by sending us a specific visual stimulation. And the reason why they could image neuronal activity is because in this preparation they put some calcium indicators. So these are specific fluorophore that becomes brighter when the neuron is in an active state. And so by looking at the fluorescence, you can look at cells, and when they become brighter, you know that at this time the cell is in an active state or is spiking. Okay, now if we have a similar preparation and we want, for example, understand how those cells are connected between them, We need to have an approach that allows in-depth cellular resolution, because as you can see here, there are some cells that have a completely isolated and precise activity. And so you might want, for example, to just illuminate this cell here and not the one around it. But now you might also want to reproduce this activity, and then in that case you need what I call here multi-scale light generation. Means that in an ideal way, without changing anything in your microscope, you would like to switch from a situation where just a single target is switched on and off to a situation where there is a number of them that has a correlated activity. And so this is what I call multi-scale light generation. And then temporal resolution is also a key point, because if you really want to reproduce with light a physiological situation, you need to evoke response in a millisecond, sub-millisecond temporal scale. And the last in the list, which will be clear during the talk, is also that ideally you would like also to deliver light in 3D. Okay, so let's start from the beginning. Can we deliver light precisely in a scattering preparation in depth? And the answer to that is something that we already know, and is to replace visible light with two-photon excitation that has been already introduced by Jens in the last talk. And the idea of two-photon excitation is simply to replace visible light with infrared light. And the reason why this allows to go deeper is because now the absorption is, the transition is made by two photons of the half of the energy, means longer wavelength, and longer wavelength is more robust to scattering. And most important, because you need two photons, this effect has an intrinsic nonlinearity. And so as you can see here, you will have a significant response only when the photons are really nicely concentrated in space, while you will kill the autofocus response. So if you compare what you have in two photon with respect to what you have in single photon, you immediately understand that you can be much more precise. Okay, so the idea of replacing visible light with two-photon excitation is to be really able to hit a single cell in your preparation. Unfortunately, this is not enough, because what I was saying before, we don't want just to hit a single cell, but we want to have multi-scale light patterning. So we want to go from a situation where only one cell is activated, but also be able to activate many of them simultaneously. And so in my lab, what we've done is to go for this multi-scale light generation, is to develop a number of approaches where this is done by a precise control of the optical wavefront. So now, before entering into the details of computer-generated holography, let me just give you a couple of slides, very basic slides, just to be sure that we all agree on some technical word that I'm using afterwards. So if you want to do wavefront engineering, the first step is that it's clear what is an optical wavefront. So this is a very classical example of a planar wave and a spherical wave. So a planar wave is a collimated parallel beam, and a spherical wave is a beam that is focused into a point. And so an optical wavefront is something that we define just to characterize how the beams propagate. And you see in this case, these are surfaces that just relate all the rays that have the same properties. In this case, they're all oscillating with the same phase. And now you see that if you want to go from a situation where the beam is propagating in a parallel way to a situation where this is focalized, you need to tilt the optical wavefront. So here now this point has has the same property of this one, and so you don't have any longer parallel planes, but you have spherical planes. So now if you want to go from a parallel beam to a focalized one, so if you want to focalize a beam into a point, you need to go from this situation to that one. And so the question is, how can we modify the optical wavefront? And then the basic way of doing that is to let your beams go through a refractive medium with a certain refractive index. And the reason why this tilt the optical wavefront is because the speed of light in a medium depends on the refractive index. So if you compare the propagation of this beam with that one, you will see that here the optical wavefront is characterized by this line here, but now this wave is delayed with respect to the other one, so at the exit this wavefront is tilted. So basically you can tilt or modify the optical wavefront by making advantage of the fact that light, when it goes through a certain medium, has the speed of light is going to be changed. And now if you want to, you can build up a system where the thickness of this material changes depending on the position, so that the central part of the rays is going to be delayed more than the side part. And so you will create exactly what we were looking for, so a situation where you go from a parallel to a spherical wave. And so your beam is going to be focalized in the point, and this magic element that you see here is nothing more than an optical lens. Now you can do the same. Instead of patterning the light, instead of playing with the fact that you are traveling to a material with a different thickness, you can play with the refractive index. So you can build a sort of refractive index lenses where the central part has a higher refractive index with respect to the side part. And again, for the same physics I was explaining you before, your wavefront is going to be tilted. And now why don't what we could do is to do this in a dynamic way. So if instead of using a static element, we use an element where you have different pixels, each of them with some liquid crystal, those materials have a specific properties so that depending on the voltage that we apply, they change the way they are oriented, so they change the local refractive index. So you can build up a sort of dynamical lens so that the central part, again, is addressed with a higher refractive index and the side part with a lower refractive index. So the interest for that is not simply to build up a lens, but is that if having this device, you can be more ambitious with respect to what you want to do with light. So you can think of pattern light in a sort of any arbitrary shape, provided that you can calculate which is the optical wavefront that you want to address on the liquid crystal matrix. Okay, so from now on, the question is, can we build up a system so that we have this total freedom in patterning the light in the sample plane, and for that, can we calculate for each of these patterns which is the optical wavefront that I want to send on the liquid crystal matrix. And actually this is possible, so it's possible to calculate this optical wavefront, and the principle that allows to do us is actually a very old principle in physics, for which in 1971 Dennis Gabor got the Nobel Prize in Physics in introducing the idea of holography. Okay, so here you can see a basic scheme for holography. So you need a laser, and you need to split your laser in two beams. One that from now on I will call the reference beam, and then you have another beam that goes through an object, and is going through the object. So now the beams going through the object, which we can call the signal beam, is going to be diffused, scattered, modified. And now if you let this beam propagating, you can fix in a certain plane, and you can look at the interference pattern that the reference beam is creating together with the signal waves. And the interference pattern is something that is represented here. So here, this is one of the first experiments in 1948 where they demonstrate the principle of holography. So this is the object, and this is the interferogram that light diffusing from this object is creating with the reference beam. And you see there are some dark spots alternated with very bright points. And now the magic of diffraction is that if you illuminate back this interferogram without having the object, actually light propagating through is going to recreate the shape of the object. So holography is nothing more than that. You have a physical object that you want to reproduce with light, and you do this by recording the corresponding interferogram. So the question now is, can we use this light to do optogenetics? So we can, but we need some technological progress with respect to this first demonstration. And this is what brings us to what is called today computer-generated holography. But the physics is absolutely the same. So again, you start by defining a certain target, and you say, okay, this is where I would like the light to be delivered. And instead of physically recording the interferogram, today you can simply calculate this because we have computers. And so you can quickly calculate which is the interferogram that light back propagating from this object will create with a reference beam. And now, once we have calculated this interferogram or hologram, we can send this directly on this liquid crystal matrix that I was describing you before, and that you know now is something that allows you to impose any phase modulation into an incoming beam. And so what happens is that now if you send the laser through the liquid crystal matrix, which has been addressed with a specific hologram, at the sample plane, the laser beam will recreate your object. So we are now very close. We can now really think of using this light for optogenetics. The only point missing is, can we be really sure that the light that I sent in the sample is really going into the neuron or to the neurons that I have selected? So for that, what we proposed back in 2008 was to use the fluorescence. So in your preparation, you have seen before that normally you have your optogenetic actuators, but also fluorescent reporters. So you can take a fluorescence picture, and on the base of the picture, decide which are the structure or the cells that you want to illuminate. So this can be, for example, in this case, a subcellular process, but can also be a precise group of cells. And this can be done on the basis of a static fluorescence picture, but you can also decide on the basis, for example, of the movie I showed before, that you want to re-illuminate neurons that at a certain time were synchronously firing. Okay, so you, in each of these cases, you will enter this profile in your calculating algorithm, and you will end up by having a certain hologram. And so when the light is going through, you see here, you can reproduce at the sample plane an illumination pattern that precisely reproduces your target. Okay, so with the principle of holography, the idea here is to really control the light so that at the sample plane is re-illuminating the structure that you have selected. Okay, so in this, we can be very precise with this approach, so we can really decide which is the structure that I want to illuminate. And to convince you about the precision, let me just show this is an experiment we did a couple of years ago, where we combined holographic patterning with a fiber bundle, and so that the holographic pattern is now transferred through this micro objective. And the advantage of having a bundle is that this can be fixed on a freely moving animal. So this indicates this was a mouse that has been co-transfected with channel rhodopsin and G-camp. And the reason why we wanted to have the optogenetic actuators and the calcium indicator is because we wanted to monitor the effect of the photostimulation. And so what you see here now we decide, okay, this is the field of view, and now I want to only activate this single neuron here. And so I start to project my holographic spot on the neurons, and at the same time, through the same fiber, we were collecting the calcium response. And you can see that at each time we send a flash, we have a nice response evoked in the cell. And about the precision, this is something you can have an idea about the precision here. So in this second movie, this is the same experiment, but now we start to place the spot far away from the target, and then we move the spot closer and closer to the cell. And you see that when the spot is about 20 micrometers far from the target, we have no response, and then the response becomes bigger, and then you reach the maximum when the photostimulation spot exactly coincides with the targeted cells. So we can really have single cell precision, so we can control activity of a single neurons in the brain with single cell precision. And we won't have time to go through this now, but if you use this approach into photon, and plus you combine this with an approach which is called temporal focusing, you can be also very precise in the axial direction. So eventually you can shape your illumination volume to exactly fit the size of a single cell. Okay, now something also that I've listed in my list of tasks was the temporal precision or temporal resolution. So this is a complicated point. So the question is, which is the temporal resolution of this approach? Actually, this has a different answer. It depends really on the preparation you have and on the channel you have and which is your readout. But from the optical point of view, actually the temporal resolution is only limited by how much time do I have to stay to illuminate my preparation to evoke a certain response, because this is a parallel approach. So no matter if you are illuminating one or 100 targets, the resolution is always this one. So how long do I have to stay on my target to evoke a certain response? And then this number ultimately depends on the expression level, the sensitivity of the opsin, and the kinetics parameter of the opsin. So here, just as an example, I pick up one opsin, which is very fast, just to show you how precise we can be with this approach. So we have been concentrating using Chronos. This is a collaboration with the group of Ed Boyden. And we were particularly interested in this opsin because it's very fast. It has a very short rising end of time. And so we measured the two-photon absorption spectra of this opsin, and then we start to see what was the temporal precision we could achieve. And actually, we have a nice action potential generation with a sub-millisecond temporal resolution, but more interesting, it wasn't shown here, where because of the fast of kinetics of the opsin, we were able to drive interneurons at spiking frequency up to 100 Hz into photon. And this was very interesting. We never reached the same precision with other opsin. And you can see here that not only the neurons spike at 100 Hz, but also we can keep a very nice precision between the photostimulation pulse and the neuronal response. So if we go back to the list I was mentioning before, so using two-photon, you can go for in-depth cellular resolution. Using holography, you can achieve this multi-scale light generation. And depending on the opsin, you can achieve milliseconds and millisecond temporal scale. Now, the last point I would like to talk about is, can we do three-dimensional light shape? So can we do all what I show you, not just in a single plane, but into multiple planes? So we need to somehow change the algorithm that we want to use. But this algorithm exists, and actually they have, at the very beginning, they have been introduced by the community of optical tweezers that really did a long job to develop algorithm that allows the generation of multiple diffraction limited spots. So years later, we use the same approach to perform three-dimensional multi-spot uncaging. And so it's actually relatively simple to have algorithms that generate multiple spots in 3D, multiple diffraction limited spots. Now, this is not the best way to activate optogenetic actuator. So you actually need to make those spots bigger. But this, again, is something that is doable. And actually, the basic algorithm exists already since 1997. So we recently, what we have done is just to implement this algorithm to create a two-photon holographic system where we can really make advantage of the entire field of view to produce a standard light shape in 3D, and this, you see an example here. So we can really control and deliver light in large volume by using three-dimensional computer-generated holography. And you can see some example here. The first proof of principle for that was in collaboration with the group of Claire Weihart at the ICM in Paris, where we used this approach for quick photoconversion of multiple cells. These were zebrafish expressing CAIDA. So you see that we can simultaneously photoconvert a large number of cells in multiple planes. This was in the spinal cord. You can achieve the same in the more scattering region as the brain. And so the reason why I'm now insisting a lot on the fact that you can produce pattern in 3D is because, I mean, if you come up with a way that to deliver light in planes which are distinct from the objective focal plane, something that you can do is to think of combining this approach with an imaging approach with the capability of completely decouple the plane from where you do the photostimulation from the plane where you do imaging. And why this is interesting, because you can think, for example, to photostimulate a certain cell population somewhere here and look at the effect of this stimulation in a plane which is no matter where in the axial position. And so this is specifically the configuration that we have optimized in order to have a system that was usable for the collaboration that we set up together with the group of Serge Picot, Denise Dalcara, and Jens Dubel, and the collaboration with Olivier Marc. So here the question of Olivier was, can we understand how bipolar cell layers are interacting with the ganglion cell layer? So can we understand how, given a certain activation patterning in the bipolar cell layer, we can change, modify, or evoke a certain response into the ganglion cell layer? So for that, you have two tasks that you need to solve. The first one is the genetic targeting, and for that was fundamental the help of Denise. So she came out with the preparation so that is it possible today to selectively put the G-camp into the ganglion cell layer. So G-camp is the calcium indicator. So is the fluorophore I was describing you at the beginning that becomes brighter when the cell is activated. And then you can selectively put an actuator into the bipolar cell layer. In this case, this was either channel opsin or Richard. Okay, this is done. So from the genetic point of view, we are able to selectively put the actuator here and the calcium indicator there. The next step is to be able to decouple the photostimulation from the imaging plane, because the idea was to project different stimulation patterns into the bipolar cell layer and look at how those patterns were activating the cells into the ganglion cell layer. And so we have seen before that this can be done if we combine a conventional two-photon microscopy system with a two-photon holographic system for pattern and photostimulation. And so the idea is schematized here. So you have the imaging path, which is always going through the objective and is always focalized at the objective focal plane, but you have a completely freedom or where you are going to do your photostimulation pattern. And so the idea was to select a certain activity pattern there and simultaneously look at the ganglion cell layer and see what was happening there. Those two layers may be separated by a distance between 30 and 100 micrometers. And so this is an example of the experiment. So first of all, you take the two-photon image in these two layers, and you need the two-photon image here to look at where are the positive cells. So on the base of this image, you can decide, okay, now I want to activate those 3 cells there. And once you have defined your excitation pattern, now you move the imaging plane upwards, and you look at which cells respond to this photostimulation, and you start to analyze the calcium response. So here you see these are 4 examples of 4 cells that were responding while we were projecting this photostimulation pattern. And you can, again, these are just preliminary data, but we have the impression that there is a pretty good selectivity. So for example, in this field of view, we are projecting 3 different photostimulation patterns into the bipolar cell layer, and while looking at the ganglion cell layer, and now let's for example pick up this cell here. So this ganglion cell here has a very nice response when we project this pattern, while for example when we change the pattern, the response goes away, and then again we have a response when we move this pattern here. So we have this is a first indication that there is a good selectivity, so we can actually see attest that the response of those cells is not the same depending on the different pattern that you project. And so based on that, now you can do a sort of projective field so that you project a certain stimulation pattern that here is indicated in orange, and then you analyze the response of all the ganglion cells that are in your field of view. And then here what they did was to select in red all the cells that responded with a delta F over F greater than 30%, and then cells that with a response less than 10%, and then the other are the non-responding cells. And so in this way you can say, okay, those cells are really responding to this kind of pattern, and now you can keep on changing the pattern. For example, this is another activation pattern, and you see that also the cell that responds have a different spatial distribution. And this is another example in another field of view, again, 3 different photostimulation pattern into the bipolar cell layer and different activation pattern into the ganglion cell layer. And now this is again is just preliminary, but something that also that they are starting to look at is how many of those cells I need to activate to really evoke a response in the ganglion cell layer. So for example, this is a pattern where we selected 3 cells. This pattern is evoking a response, for example, in these 3 cells. This response can be also pretty high. But now if you just sequentially go from one spot to the other, so the 3 spots are not projected in a simultaneous way, then you see that the response is completely gone. So this is probably a mixture between the nonlinearity of the coupling between these 2 layers and the nonlinearity of the calcium indicator. So it's just an ongoing project, but it's just to tell you that to record a certain response is anyway crucial to have at least 3 of those cells simultaneously activated. Okay, so this is time to conclude. So what I wanted to convince you is that you can combine computer-generated holography and optogenetics to achieve single-cell resolution in the photostimulation pattern, millisecond temporal precision, and multi-scale light patterning. So here I've been particularly concentrating in showing you some example where this approach can be used for investigating the retinal circuit. But of course, there are other applications you can think of this kind of approach. For example, this can be used for uncaging, can be used for cell inhibition, for cell ablation, and also what I show you in the experiment with Claire with protein photoconversion. It's okay, most important, the people that has been involved in the data I show, so the people in my lab at present and in the past, and specifically the experiment in the retina have been carried out together with Giulia, Olivier, and Emiliano Ronziti and Irini in my lab. And then Oscar, together again with Irini, they worked in the development of this algorithm to perform 3-dimensional holography with the help of also of Marc Guillon. Vincent Desarts, he designed and built up all the software to control the liquid crystal matrix combined with two-photon microscopy. Of course, I thank the many people that are financing my lab, and thank you for your attention.